Scaling a modern, multi-tenant cloud architecture across highly complex, interconnected enterprise environments inherently introduces severe structural networking bottlenecks. For years, engineers have relied on Layer 3 VPC peering as the baseline standard for bridging isolated cloud networks. This diagram illustrates the inherent structural flaw in that approach. When you peer two VPCs, you are forcing the native merging of their routing tables across different organizational boundaries. This relentless merging drives infrastructures straight into the hard limits of the address space, specifically the exhaustion of the available RFC 1918 IP blocks. As large organizations integrate, overlapping CIDR blocks inevitably collide. A single overlap results in routing rejection, as the control plane cannot resolve two identical paths to different destinations. Early stopgaps like legacy private service access exacerbated this friction by demanding massive, rigid subnet allocations just to provision managed services. Attempting to resolve these collisions via traditional NAT gateways or complex route filtering creates unmanageable latency and operational overhead. To maintain multi-tenant scalability, the architecture must decouple the service transaction from the underlying Layer 3 routing domain. Private Service Connect is an SDN abstraction layer, abandoning Layer 3 routing. A consumer endpoint IP is deployed in the consumer VPC, mapping to a producer service attachment. Packets route to the local endpoint, where the SDN control plane executes strict encapsulation across the gap. That connectivity relies entirely on a dedicated PSC NAT subnet, using source NAT or SNAT on the producer side. In this detailed view, we can see how SNAT maps the incoming traffic directly onto the producer's network, stripping away the consumer's original IP address. Decoupling the consumer IP from the producer's routing domain protects the internal network topology from complex external dependencies. Consider a concrete production scenario. An enterprise consumer needs to connect to a SaaS vendor's external analytics service hosted in an entirely different GCP organization. A critical systems conflict exists. Both the consumer and the external vendor are utilizing the exact same 10.10.0.0/16 RFC 1918 IP block. On the left, traditional VPC peering fails. Merging routing tables with identical subnets creates a technical block. On the right, we deploy PSC. Notice there is no Layer 3 peering line. The consumer provisions a single endpoint IP within their overlapping CIDR block. This single endpoint creates a direct logical mapping to the vendor's service attachment. When the consumer VM initiates communication, it routes strictly to that local endpoint. From there, invisible SDN encapsulation bridges the distinct environments. The necessary SNAT translation occurs exclusively inside the vendor's dedicated PSC NAT subnet, allowing the packet to complete its path without IP conflicts. This discrete endpoint-to-backend translation resolves the IP collision. The entire transaction is divorced from the consumer's original IP space. This topology map illustrates a standard hybrid architecture, an on-premises legacy data center connecting to centralized cloud infrastructure. The physical connection medium here is a dedicated cloud interconnect, linking the on-premises routers directly to the central Hub VPC. On-premises applications query databases isolated inside spoke VPCs. Traditional transitive routing is inefficient. Configuring routes across all spokes exposes massive subnets, creating a fragile topology. The PSC alternative is highly surgical. We provision a single PSC endpoint IP directly inside the centralized Hub VPC. The on-premises legacy routers only need to learn this single endpoint IP. In this diagram, we see the propagation occurring via standard BGP advertisements, traveling over the interconnect. The massive spoke CIDR blocks are intentionally excluded from being propagated down the interconnect. Importing only a single /32 IP address explicitly isolates the spoke networks, limiting the corporate network's blast radius to one endpoint. To understand the efficiency of this model, we execute an explicit comparative structural analysis of PSC versus legacy private service access. Legacy Private Service Access, or PSA, imposes heavy architectural demands. In this structural comparison, PSA forces engineers to allocate a massive, rigid CIDR block, such as a /16, specifically to consume managed services. This monolithic allocation rapidly accelerates RFC 1918 exhaustion, forcing architectural lock-in. We contrast this directly with the modern endpoint and backend model of Private Service Connect. In this updated model, PSC relies strictly on single/32 IP allocations, eliminating the need for massive subnet carve-outs. Despite this micro-allocation, the architecture maintains surgical line rate performance. PSC delivers necessary managed service connectivity with zero shared routing dependencies, preserving an organization's IP address space. Zooming out from specific failure states gives us the macroscopic view of an asynchronously decoupled global cloud topology. Systems engineers are no longer constrained by the necessity of merging monolithic Layer 3 environments. Consuming external and multi-tenant services does not require exposing internal routing tables. This is achieved entirely through SDN abstraction and a discrete endpoint-to-attachment architecture. Source NAT implementation resolves CIDR overlap by translating source identifiers at the producer boundary, ensuring traffic flows cleanly across the endpoint bridges. This model grants architects control over hybrid BGP routing propagation across dedicated interconnects. Modern network design requires decoupling structural dependencies. Defaulting to PSC over peering or PSA protects finite IP address space and hardens the network's blast radius against systemic failure.